Yep. Tiger 9-1. Tiger 9-1, Roger. Anchor 26, Iskra, claw 035.
And today on the bench we have the latest smart tweezers from smarttweezers.com. Let's take a look. They arrive in a nice box. This is the unit right here, and I'll try and get some pretty good close-ups of this. It has a bright OLED display, easy to read at a reasonable distance, and certainly very sharp and clear, high resolution. Comes in a little with a little slip case here, which works quite well, and it is a USB chargeable. This is a small lithium-ion battery in it, and so it comes with a nice little convenient charging cable. And of course, always need instructions, but it's quite intuitive. I don't know that you'll really need these, but pretty straightforward to use this, and information about the how it all works. Well, all right, let's turn it on and watch it boot up. And that's it. Very nice little display. High res, and it's very bright. This is the test current, and it remembers what you last set it to. Same with the pulse width, how long the LED would be on for, and the battery indicator. And this little asterisk down here means that it is searching. If I close the tweezers and short them, it figures that out, and it does a little beep. And when we test it with an LED, it figures out the polarity and the voltage drop. So it's pretty simple, very straightforward, easy to use. This is a little joystick, so just press the button to turn it on, and then press upward on the joystick or downward to change the current settings, left to decrease the pulse width, and it automatically loops back to 1 full second, 1,000 milliseconds. Pressing left decreases, pressing to the right increases it. 10 millisecond is the minimum pulse width, and 1 millisecond is the maximum. Now the test current options are from 1 milliamp up to 30, so you go to 2 milliamps, 5, 10, 20, and 30. And of course back down, but when I get to 1, I can press it again and get to 0.1 milliamps, and there's no decimal point in there. I can't tell if that's supposed to be 0.1 milliamps or 0.01 milliamps, or is it really just some sort of exception condition I've created. But let's try it out. So I'll set the unit to 5 milliamps, and let's see if I can get everything on camera here, or at least everything important. And the pulse is a little short, so I'm going to increase the pulse width to a couple hundred milliseconds. There we go. You can see it immediately locked on, and I'll try to hold it all on here. It figures out the polarity. So this is clearly the anode, and the cathode are clearly marked. And then it's a 1.7 volt drop, 1.71. And that works really well. And of course, if I push that out to the right, I can get a much longer pulse. And I can decrease the brightness a little bit by just dropping that down to 1 milliamp. You can see it's a little less bright, the display is, or sorry, the LED is, but not by much, because it's a pretty low current device. There we go, 10 milliamps, it's really cranking. All right. Next up, let's try maybe something big, a little heavier. There's a blue LED. And we'll turn that off to the side there. 2.49 volts is its drop, and we're testing it with 10 milliamps. We can certainly drop that down to 2 or 1, and we can see that it definitely lights up. And we'll go up to 20. I think that's the limit for these LEDs, is 20 milliamps the ones that I have here. And if I switch to the next one down, it has the reverse polarity. So this one is anode and the bottom is the cathode. I go to this one, it has instantly detected that, and it's working great. This would have been handy to have a while back when I was making little LED breakout boards that I use on breadboarding, because at the time I ended up with a bad LED installed on one of the breakouts, and a couple of the LEDs swapped around. So this would have been great. So how does it do this? How does it figure out the polarity and the working voltage of the LED that's under test? Let's see if we can run some tests or take a look at that. So I have a little test jig now, and right here we have the LED, and I've connected the scope probe ground clip to it. I have one probe connected to the anode, the positive side of this LED, and then the negative leg, the cathode, has a resistor to it. This is a 100 ohm resistor, so that might affect some of my results on the screen there. We'll see. And over to another probe, and what we're going to do is run the power through to the LED this way, and that will make this the negative, this the positive, and we'll get a small voltage drop across this 100 ohm resistor, and hopefully that won't really skew the test results. But we've already measured it, so we really know the results on this LED. We just want to kind of see how this thing works. And what we're going to do is check it all out on a scope and see if we can't find something interesting going on. Alright, so we have our test set up. Make sure we're actually recording on everything. And if I connect this up, we get a nice blinking LED. 2.48 volts is the drop, so it altered it just a little bit with that 100 ohm resistor. There's not much of a voltage drop there. And we're showing the settings. We've got it set to a half a second. I don't really need that, so I'm going to drop that down to 10 milliseconds and get some little pulses. And hopefully I can keep this all set and running down here while we look at the screen up here. At this point, let's take a look, and I will run this to single shot mode. Ah, there we go. Got some data. Let's move that up a little bit and do it again. All right, what we're looking at here is the green line is channel 2, and that is the current. And right now, because of how this is set up, the current is going to show negative, and because of the way the probes are set up on that. Here's the voltage. So first off, the voltage sweep comes through. Let's turn that off. Here we go. The voltage sweep comes in. The probe does a sweep on the voltage, and it goes negative. I should turn off that touch, shouldn't I? Probably. Comes in, does this, gives a negative pulse, and then says doesn't find anything, gives a positive pulse, and sure enough finds it, and then amps it up. At least that's what it's looking for. So it cycles negative, then positive, and it's trying to find out which direction the polarity is, it looks like, of that signal. So here's the whole thing, and it looks like we're at, per division, we're at 10 milliseconds, so there's our 10 millisecond pulse. Now, to turn on channel 2, and run it again, there's our negative going voltage, and here's some sort of a positive pulse, or signal from the on the current. And you can see these big current spikes. Not sure if I'm getting accurate measurements, but I think so. So if I run that again, we can see the as the voltage comes back up, we get a little current spike there. So we've got a 2.27 volt peak to peak right here on this thing. So now some of that's going to be this little spike here, and we have this spike here. I'm guessing this is probably, well, let's just take a look. 1, 2, 3, and about half a division. And on channel 2 we're at 500 millivolts, so we're looking at, that would be 17.5 milliamps right here in this pulse. That's pretty good size considering we had it set to 10, but it's a stunningly short pulse. These pulses in here are really very short. And then you can see the actual ramped up current pulse for the actually blinking the LED here. So that is interesting. I'm going to have to look at that a little bit more. So what I found is at 500 nanoseconds per division, here's that one of these short current pulses. They are short. We're getting we'll call it one division, so about 500 nanoseconds. It's very sharp here, probably 200 nanoseconds from zero to peak, and then it fades out, and that fades out over the course of about 3 divisions, or about 1.5 microseconds right here. So it's actually really short pulse. No wonder they're able to get away with this here, as we see the very short pulses in here that probably isn't going to damage that LED at all, allowing a little higher current pulse. And that's where and the reason that's happening is they're doing this voltage spike, trying to figure out at what point this LED is going to turn on, and they figured that out here. Let's look at that LED one. Right here, we see the top is 2.47. Well, you know, that's what we measured as the drop right across that LED. So this is 2.47, and that's what they measured as the device measured. So pretty good. Now it's 8.4 or something is the negative and positive samplings. But here you can see that the positive value from 0 to the peak there is 2.47, and yeah, that's how they do it. Interesting. And now it's time for the obligatory teardown, and let's just see if there's anything exciting in here. I expect that there isn't a whole lot going on. There might be an ASIC. Now this should just remove the back of the case, and there we go, or the front rather. And there's our display. There's an interesting little mechanism down under here, which I'm hoping not to disturb, because I think they have a pretty cool little mechanism in there. But looks like I'll have to take that screw out after all to get a little further. Well, that screw is definitely a Torx T5. I hope I don't pop this whole hinge mechanism loose and mess this up. I have to figure out how to put it all back together. Right, there it is. Oh, we popped a very, very small JST connector loose in there. There's a very tiny battery. Well, actually, it's not too bad. 180 milliamp hour lithium battery. And then here's the mechanism. Okay, I thought there was a more complex hinge mechanism going on in here, but that's not bad at all. That's just just basic stuff there. Okay. So that's what's in there. Small battery. On this side, I'll try and get under a microscope or something and take a little closer look at the chips. So what do we find under the hood? Well, for starters, here's our little USB connection, and it looks like there's not just power but maybe data hooked up, but I'll have to take a closer look under there. Although when I hooked this up to a PC, no file system showed up. It was just charging. First off, we've got a couple of small SOT-23. So we've got I think this is probably a PNP device here, and then up here, I'm not sure what this one is. Could be a charge controller, actually, and that's probably what it is, because this is a JST connector for the battery. And hobbyists will appreciate this. This is a nice big MSP 430 chip. So very impressed with that. There's certainly a lot of capabilities that could be added to this device with a chip this powerful under the hood, and especially given what it's doing, LED testing. So it should be able to be you should be able to do all kinds of neat stuff with this, maybe in the future. Over here, this is probably the boost converter to get the battery, the lithium battery's power up to into the 5-volt range. So we've got a large, well, actually, it's actually a pretty small inductor right there, and then this is probably the boost controller, probably a FET for part of that, but I'm not sure. Then we get down into here, and I think these are some maybe some diodes set up out here, or they could be more transistors hooked up. Let's see. I think this one's actually probably a dual NPN right here, and this is a dual PNP, if I had to guess, but not really sure quite what everything is under the hood. And then again, this one I didn't find any notes about this. These are where the contacts come in from the tweezers, and this could be just an analog switch, maybe that's what this is. Certainly would kind of make sense to do that, but I don't know if it would. If a lot of the analog switches would be able to switch up to 30 milliamps through there. Maybe. Anyway, that's what's under the hood. So you've got the tweezer contacts coming in to a small analog, probably an analog device right here, and then some NPN transistors. This could be a digital device that's used to control the transistors here. These might be hooked up in some sort of H-bridge arrangement to drive this. And then it's all run back to the MSP 430, a little power boost converter, battery controller, and battery connection, and then of course the USB connection. And on the other side, what do we find? Well, there's a little can right here that seems to be just a support. It's glued down. There's an adhesive strip connecting the display down to that, and that really doesn't seem to have anything under it. I've shined a light. I did shine a light under that, and it looks empty. And then otherwise under here, we've got just the little flat flex connector, and probably looks like a row of capacitors down there. So not much on this side, and of course the joystick for the menu controls. It's a little hard to get a good focus on it. It looks like this board is like 10 layers. I don't think it really is, but the striations in it indicates that it's clearly there's clearly an inner layer going on this, because this side is just a complete pour pretty much, with the exception of a little bit moving around on it. So it's probably there's probably at least one inner trace layer on here, but that's just my guess. So anyway, that's the inside. Well, I want to thank the guys at Smart Tweezers. That's advanceddevices.com. It's made in Canada, so just up north the border a little ways, for sending me this for review. It's a really nice little device, and like its sibling, the LCR meter, it's ergonomic, well-made, really a nice little device, well-engineered, I think. It's not the cheapest, but if this is at $89 list, I believe. But if this is something that you're likely to use on a regular basis, I think it's a pretty nice little device. It does what it needs to do, does a good job of it.